So welcome back from part one. So this is going to be part two of showing a recursive sequence, in this case would converge. And the next thing we wanted to work on with this problem was to show that it was decreasing. So decreasing means that a sub n plus 1 is less than or equal to an, given a sequence an. In other words, given one term of a sequence, it's less than or equal to the previous term. Okay. Now, three ways of proving that. The first method here, let me rewrite what I have for number one, is by showing that a sub n plus 1 minus a sub n is less than or equal to 0. And that's just like a take on this by subtracting a sub n on both sides. Second method is if your terms are positive and if your terms are positive, then you can show that an plus 1 over an is less than or equal to 1. And the third method is using calculus here for certain types of sequences. So I'm going to be working with that first method, an plus 1 minus an is less than or equal to 0. Okay, and let me go ahead and get started on that. So an plus 1 minus an would look something like this right here. So I replaced the a sub n plus 1 with what the recursive formula tells us it is, and I kept a sub n as that. Now, what we can do here is a few things here at our disposal. One thing is to multiply the top and the bottom by the conjugate. So yeah, technically what I mean by, I make a fraction by dividing by 1 and then multiply the top and the bottom of the conjugate by the square root of an, square root of 8 an plus 9 plus an. So typical algebra move here. And the top would become 8 times a sub n plus 9 minus an squared after I multiply by the conjugate. And here's what I'm going to do. I'm going to factor the numerator. And it gets us to this point right here. We have the expression 9 minus a sub n times the expression 1 plus a sub n all over the square root of a sub n plus 9 plus an. I want us to concentrate on the numerator for a second. In the part one, we proved that a sub n is greater than 9. So therefore, 9 minus a sub n is going to be less than 0. Okay? Yeah, because if you have terms that are bigger than 9, if you subtract them from 9, they're going to be negative. So therefore, this whole expression right here is going to be less than 0, but that's what an plus 1 minus an looked like. So it's less than 0. Okay? And therefore, an plus 1 is less than an, it's decreasing. And since an is decreasing bounded below, it converges by the monotone convergence theorem. Now the question now is, what does it converge to? Okay, so let me go back to the sequence, the formula we have. And here's what we're going to use. We're going to use this fact. It's really a theorem, but which says the following. Something you can prove somewhat quickly. But that's not what we're going to do. We're not going to do that today. If you take the limit of a sequence that you know convergence, then the limit of the sequence, which you get by just shifting the terms by 1 here, is you get the same thing basically here. So if you shift a sequence by 1 unit, or whatever number of units, and if that sequence converges, it's still going to converge, maybe a little faster. That's all this theorem basically says. So should put the word then here. So here's what I'm going to do. I'm going to take the limit of both sides. And using a property of limits of sequences here, we can also do this. So yeah, sorry, adding an extra layer here. We can do this as follows. This equals L. This would equal the square root of 8 times L plus 9. Yeah, because if you take a sequence and you multiply it by a number, the sequence converges, it just converges to whatever that number in front is times the limit, so 8L, and then plus the limit of a constant is just a constant, so that's why they have that 9 there. So this is what your equation gives us. So if you square both sides, you get 8L squared equals 8L plus 9, L squared minus 8L minus 9 equals 0. If you factor this, you get L minus 9, L plus 1 equal to 0. So L equals 9, or L equals negative 1. And because our terms are positive, the only possibility here is that L equals 9. Okay, L equals negative 1 is really just an extraneous solution that we get here. And there we go. So now we know that our sequence converges to 9 officially. Okay. The one note that I wanted to make here is that with the monotone convergence theorem, we're using the theorem to prove that it converges. But that does not help you to prove what it converges to. Okay. Seeing what it converges to, that goes back to the beginning of our sequence here. And that's where we put numbers in. So we basically, put some numbers into our sequence from part 1, looked at a calculator, and we saw that it looks like it would converge to 9. But again, that's all we had at our disposal. We didn't know that whether it was going to converge. That's where the monotone convergence theorem helps us out. But the theorem itself doesn't tell you what it converges to, and so we had to officially use all this right here. And yeah, the only way I could make the statement right here is by knowing that it converges. A lot of people, when they're working with these problems, they'll actually skip right to this. But the issue with that is that, yeah, you don't know whether your sequence converges or not, so you can't technically say that it equals a limit. All you're doing there is saying if it does equal a limit, then what you see here, you can make this argument. That's all we're saying. Okay. All right. Well, thank you very much for your time. Appreciate it.